Example 12.5 says, using the graph below, determine the function's equation in both vertex and standard form. So all we're interested in here is writing the equation. We're not trying to write the entire function definition, just the equation, but we are being asked to do so in two forms, both the vertex form and the standard form. The vertex form we know would be f of x equals a times x minus h squared plus k, and our standard form, which was the first form that we discussed in this section, is that ax squared plus bx plus c form. So looking at the graph, there are certain things about this that would help us to be able to write out the equations. Now, if I want to be able to write the vertex form, then I should be able to come up with a value for a value for h, and a value for k, and then I would just substitute those things in, and I have it done. Same idea applies for the standard form. If I can figure out what a, b, and c are all equal to, then I can just substitute them into the form, and I've got it done. Certainly the nice thing about the vertex and standard form being equivalent to each other is that the a value for one is going to be the same a value that you would use in the other. The only thing that's different is that b and c are not going to be the same as your h and k. Those are going to be different. So looking at the graph, there's a couple of things here. First thing I notice is the location of the vertex. The vertex is located at -2, +3, which represents the value of h and the value of k. So that's 2 out of the 3 things that I need to be able to write my vertex form equation. The only other thing I need is the value of a. So if I think back to example 12.3, 12.4, and even 12.2, where we were graphing based off of the equation, we were able to do 2 things with a. A allowed us to determine if the graph opened up or down, and it also allowed us to determine if there was a stretch or a shrink. So looking at this picture, I need to determine, is there a stretch or a shrink, and what is the direction that it opens? And that should give me a clue as to what a should be. So looking at the vertex, I'm going to go over 1, down 1. Go back to the vertex, I would go over 2, down 4, which shows me that there is no stretch or shrink. This is just the standard parent function, but I would certainly say that it opens down and not opens up. So when it opens down, that means that my a value will have to be less than 0. It's going to have to be negative. But since there's no stretch or shrink, that means that my a is supposed to be 1. So if it's going to open down, but it has to be a 1, that means I need to use -1. So that same -1 can also be used over here in the standard form, but I don't have the information about b and c yet for that. But let's just pause for a moment, and let's finish up what we have here for the vertex form. So f of x is going to be equal to -1 times x minus -2 all squared plus 3. So that's what we get when we just directly substitute in the a, h, and k. And the only thing that I would really do here in terms of cleaning it up is the x minus -2. I'm not crazy about leaving it like that. So instead, I would just write it as x plus 2 all squared, and then I'll put the plus 3 there at the end. And that represents the vertex form version of the equation for this graph. And then for standard form, we're missing the value of b and c. And without the value of b and c, it's going to make it really difficult to write the standard form equation. We talked about at the beginning of the section how to go from standard form to vertex form using complete the square. What we haven't done yet is discussed how to go from vertex form to standard form. So what I'm trying to say here is that we don't have to try to completely build the standard form equation from scratch. Why not just use the result that we currently have for the vertex form? Since the two formats are really representing the exact same function, they're just different versions of the equation, I should be able to use one to get to the other. So that's what we're going to do. We're going to take the vertex form that we came up with, and we're going to use that to get to the standard form. And you are not going to need anything as complicated or as sophisticated as completing the square. The only tool that you need is order of operations. That's it. So if you use PEMDAS to help you remember the order of operations, that's what you're going to use. So that means we need to start with the exponent as it applies to this parenthesis. So the -1 multiplier is going to stay out in front, and then I'm going to square x plus 2. That's going to result in, well, it's supposed to be x plus 2 times x plus 2. That's what the definition of squaring means. So if I go through the distribution, or some of you will call that a FOIL, I would get x squared plus 4x plus 4. Tack on the plus 3. Now I'm going to distribute -1. So I'll have negative x squared minus 4x minus 4 plus 3. And then finally, combining the like terms at the end, negative x squared minus 4x minus 1. So we didn't have to find b and c to be able to get the standard form, but now that we have the standard form, we can see that b is -1 and that c is -1. A is -1, b is -4, and c is -1.